Welcome to Microhard session number 6 at Xcoder Video. We appreciate your coming to watch this. In this video, we're going to take a look at the full adder. In session 5, we looked at the half adder and created that component. And I thought that since we've just looked at binary operations and the half adder, that we ought to go ahead and look at the full adder. That was the new task that was given to us after creating the half adder. Makes sense to do it now. You'll recall in that we discussed, let me get this off. We discussed the 1-bit addition in the last video, and we saw how the half-bit adder was able to perform all of these operations. I've summarized that a little bit in this full adder logic document. And the full adder is identical in function to the half adder, except that it considers a possible carry operation from the previous column. The half adder can perform the following 4 operations. That is where we add 0 to 0, 0 to 1, 1 to 0, and 1 to 1. There are 2 outputs for the half adder, the sum of the first column digit and a possible carry bit. The full adder, on the other hand, can perform all of these operations and plus 4 additional operations that we see here. In this representation, the 4 ones at the top of each column are carry operations from a previous calculation. That's conceptually how they work. And the half adder can supply an answer only to single-digit addition operations, but by chaining several full adder components together, the full adder can add multiple columns of digits together, including any carry operation that the addition problem requires. Let's compare the truth tables for the half adder and the full adder. This is the truth table from the half adder. There are 4 cases, 4 different inputs, 0, 0, 0, 1, 1, 0, and 1, 1. And these are the possible answers, outputs for the sum and for the carry, depending upon what's in the inputs. The full adder table is just a little bit more complicated because it has an additional input, which is the carry in bit. The first 4 cases are identical to the first 4 of the half adder table. The last 4 operations differ in that we have a carry bit coming in, and that changes the sum and the carry operations to what we see here. If you'll notice, there is 1 bit here in these 3 bits, so the sum is 1. There are 2 bits in these 3 inputs. 2 bits has a 0, 2 bits are represented by 1 0, and so we put the 0 in there for that column, and then we give a 1 for the carry. This next line is also 2 bits, so it gets a 0 and 1 for the carry. And then in the case where both of the add-ins are 1 and the carry is 1, that produces a 3, which is represented by 1, 1, the first column, or the column where the operation is taking place gets a 1, and the carry gets a 1. And that is what the full adder truth table looks like. There are a number of ways that the full adder can be implemented, and depending upon the available components that you have, perhaps the simplest design is what I've given here, though it's may not be the most efficient design. In the full adder has 3 inputs: the carry in, add in 1, add in 2. These are equivalent to N1, N2 in the specifications. And the inputs are, in the case of this design, the inputs, some of the inputs go to the components just as they are, and the inputs also are negated and go to some of these components like this. There are, it looks like about 10, 11 AND gates here, and about 4 OR gates to complete this circuit out. And if we run this and look at how how this works, we'll be able to see how the sum and the carry operation work. And so if the add-in is 1, the sum coming out, that's a 1. If we have both of the add-ins on, then the sum is 0 and the carry is 1. If the carry is 1 and both of the add-ins are 0, the sum is going to be 1 because the carry bumps it up. If the add-in is, if one of the add-ins is 1 and the carry bit is turned on, then the sum is going to be 0 and the carry is going to be 1. And if all 3 of them are enabled, then the sum is going to be 1 because this equals to 3. These 3 bits equal to 3. And we're adding 1 plus 1 plus 1 to get 3. So that gives us the sum of 1 and a carry out to the next column. And that's the way the full adder is supposed to work. So let's take a look at what the specification tells us here. We've got 3 inputs: carry in, N1, N2, 2 outputs, out and carry out. And the truth table, this is just a partial truth table down here to show you several examples of what the output should look like. And we're going to come back and take a look at the design in just a moment. But first, I want to come back over here. No, I don't want to quit the Microhard destination. Let's take a look over here. I want to go to the settings folder and look at statistics. These are the logic circuits that we've created so far and the score that we have that we got for each of the circuits that we've created. Notice that other individuals who have made these same circuits have created more efficient circuits. For example, the R16B, whereas I got a score of 160, someone got a score of 64, almost 100 less than the score that I received. And what this means is he was able to come up with a design that involved fewer components and possibly faster speed than the design that I've received with the exclusive OR. Sometime in the future, we're going to want to go back and look at these components that are inefficient for me and see if we can't optimize those components. And when we do that, we'll come back and talk about how to optimize at that point. But let's go ahead and go back to our full adder specification and go ahead and get into the design. Going to just clean this up a little bit first. Then we'll come back, and we've got a lot of parts to define. So let's bring up our diagram here and see exactly what we've got. We've got 3 NOT gates. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 AND gates, and 4 OR gates. So let's go ahead and define those. I'll pull this over here, and let's get NOT 1, NOT, and I think I'll just do some of this on one line, single lines, to not to take up as much space as we've been before. NOT 2, NOT 3, NOT. And I said 11 AND gates. And 1. I'm going to do it AND 0, 1 so that all the labels are the same length for the ANDs. And let's see. In this case, let's try to make this a little bit easier. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And we're going to come in here and at 1, 0, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. And now let's clean up a little bit. That's 4, 5, 6, 7, 8, 9, and 10, and 11. That's good. And we said 4 OR gates. So we're going to have OR 1, OR 2, OR 3, and OR 4. And I believe that's all of the components that we need. So we can come in here and close that. The next part is going to be the wiring. And this may take a little while, so I think I will pause the video and do some of this work on my own and then come back when we get the wiring complete. We'll discuss the wiring a little bit then, and then run the test. So stand by, and we'll be right back. All right, I have just a little bit of progress to report. So let's take a look at the graph and see how it compares to the wiring that I've done. You remember the carry in is equal to the carry in here, and add in 1 is equal to N1, and add in 2 is equal to N2. And so what I've done is I've gone in and labeled each one of these components so that I know what the components are that I'm working with. And I've wired up these 7 AND gates so far just by looking at where they wire into the carry in, add in, add to, and did the work here to wire it in here. So in the case of AND 1, for example, AND 1 ties to N2, directly to N2, and it ties to the carry in through the NOT gate. This is NOT 3, this is NOT 1, and this is NOT 2, the way that we have defined our parts and wired up the carry in here. We wired up the carry in to NOT 3. So now I've got NOT 3 out to AND 1 dot N2. So just as a panic check, I want to make sure that I've got all 7 of the AND gates referenced here, and 1 and 1, and 2 and 2, and 3 and 3, and 4 and 4, and 5 and 5, and 6 and 6, and 7 and 7. So all 7 of those are referenced. And to make sure that I did them in the correct order, I've got N2, N1, N2, N1, N2, N1, N2, N1, N2, N1, N2, N1, N2, and N1, N2. And so that is correct. And as long as I've tied into the right pin over here on the left, then this part of the logic should be fine. I'm going to pause again and go ahead and get this next column, these 5, maybe all of them, but let's see how that works. Okay, I'm back, and I've filled out a little bit more of the logic for the wiring, and had quite a surprise when I got down to the bottom of the screen. I had, you remember, I had these values spread out a little bit more, where each one of these lines was on a line by itself. And I got down to the bottom of the screen, and the screen does not scroll. The last character on the line is whatever is on that last line, and you can't go beyond it. So, for example, if I bring the cursor down here to the bottom, I can't hit enter, enter, enter. It won't go any further than that. So I had to close up some of the white space in the wires in the wiring and in the parts list to get more room for the rest of the design. I continued to, well, I removed some of the comments that I used for the first part, but I continued to use the comments so that I could make sure I was getting each one of the components in the order that I needed to do them in. And so what I've done is I've completed the logic for this column of gates, this column, and this column in the wiring that you find here. The only thing that I have left is the out gate. So let me get a little bit more room up here. See if I can get my cursor up here and do a little bit more scrunching up, get me some more room. I'm going to come down here and put one more comment, and this is going to be for the outputs. And the outputs are the outputs from R5 and R4. So R5 is the sum and R4 is the carry out. So let's go ahead and put R5, no, R4 is the sum, that is the what we're calling out in this specification, and R5 out is the carry out. And if everything has been done correctly, that should work. So let's go ahead and clean this up a little bit more. I'm going to go ahead and remove these comments because they serve no more purpose. I do hope eventually that scrolling will become allowed, because I don't see how we're going to specify more complex components than this within the space that's allowed within the workspace. So let's hit Control Enter and run the test. And it tells us that the verification has failed. The device referenced by N9, N2 does not exist, so I get a little bit of fat fingering there. So let's go ahead and find out where did I have N9? It's got to be in here somewhere. And let's try that again. Still failed. Out 10. Yeah, I noticed that when I was doing it and forgot to fix it. So let's do it again. Still failed. Following errors. Too many incoming wires on pin and one N2. Okay, let's and one N2. Too many incoming wires. And one in and one in one, not 3 out and 1 in 2. And so let's see. And 1 in 2 gets its input from not 3. So that one's correct. And somewhere I've got a reference to and 1 that should not be there. It's a mistake. And 1 and 1 and 1 out and 8. Yeah, I don't see it, so let's see, look more closely. And 1 in 1. I think, can I do a search in here? Navigate words. Autocomplete? No, there's no search. Okay. And 2, and 2. 3, and 3, and 4, and 4, and 5, and 5. And 6, and 7, and 7. And 8. And 8. And 9, and 9. And 10. And 11. And 11. Oh, there it is. That should be and 6. And 6. Let's make sure that's correct. And 6 gets an input directly from N1 and carry in. So let's see if that's right. And 6 no, that can't be right. And 7 out. and 7 out is to OR 1, not AND 1. That is OR 1, not AND 1. That's what's wrong. Okay. And 6 out to OR 1 in, and 7 out to OR 2 in OR 2. Okay. Let's try our control enter again, and we still failed. All right, let's see where are we falling down? Okay, let's see. Carry in, that should be 1, 1. That should be 1, 0. Carry in, out 1. So, looks like the failure, okay, somewhere I've got the wires crossed. Okay, why don't we, let's see, I want to go, okay, let me, I'm sure that the adder logic is correct over here, but so I must have the wiring wrong. If I run this test, this test is based upon this truth table where the carry in here and the add in input 2, and so on. This is the sum should be 1 for odd numbers and 0 for even numbers. 0, 1, 1, 0, 1, 0, 0, 1. So the sum is correct. The carry out should be even for numbers 2 or greater. Or I mean 1 for numbers 2 or greater. So 0, 0, 0, 1, 0, 1, 1, and 1. So that's correct. If we run the test, we'll get the test results. Everything passed. So this is correct. The logic is correct. My wiring must be off somewhere. So I'm going to have to go through and check that wiring again. Give me one moment for that, and hopefully we'll get that corrected. Well, you might not believe this, or you might. Either way, the error apparently in my logic is that I wired up OR4 to the out and OR5 to carry out, and that's opposite from what it should be. It should be OR5 is the output and R4 is the carry out. So let's reverse those, and hopefully this will correct the error. And let's see, Control Enter, verification passed. So that is, I think that's enough for today's session. And let's go ahead and see what happens when we click OK. Get some new tasks. What is it going to give us? A new task unlock, the adder 4B. All right, this is a bus adder, and so that's I believe this what this will be is a 4-bit addition operation, and that'll allow us to use our full adder the way it is supposed to be used. When we come back, I think we'll do the adder 4B next, and see if we can't create that with a little more ease than we did with the adder, the full adder that we did today. Appreciate you watching. If you like this, please give us a thumbs up. Look for me on Steam as Xcoder, first name Gil, and I'd love to see you there. Thanks again.